Right now, you're sitting still, not moving, not going anywhere. Maybe you're on a couch, maybe at a desk, completely stationary, but here's the thing. You are moving. Right now, at the speed of light, not through space, through time. Every second that ticks by on your watch, that's you, hurtling through the time dimension at 300,000 kilometers per second. And that single fact explains why nothing can ever go faster than light. But to understand why, we need to go back to a time when nobody even knew light had a speed. For most of human history, people assumed light was instant. You open your eyes, the world is just there. No delay, no travel time. Light was simply everywhere, all at once. Galileo tried to measure it in 1638. He put two people on hilltops about a mile apart, each holding a covered lantern. The idea was simple. One person uncovers their lantern, the other sees it and uncovers theirs, and you time the round trip. It didn't work. The distance was too short. Human reaction time was too slow. Light was impossibly fast. Galileo could only conclude that if light wasn't instant, it was at least extraordinarily rapid. Then, in 1676, a Danish astronomer named Ole Rømer noticed something strange. He was working at the Royal Observatory in Paris, timing the eclipses of Jupiter's moon Io. Io orbits Jupiter like clockwork, disappearing behind the planet at regular intervals. Rømer had tables predicting exactly when each eclipse should happen, but the eclipses kept arriving late. Not by a little, by about 22 minutes when Earth was on the far side of its orbit farthest from Jupiter, and when Earth was closest to Jupiter, the eclipses arrived early. Rømer realized what was happening. Light isn't instant. It takes time to cross the extra distance when Earth is far away. He calculated a speed of roughly 220,000 kilometers per second. Not perfect. The modern value is about 36% higher. But it was the first proof in human history that light has a finite speed. Fast forward 2 centuries. By the 1880s, physicists had refined the measurement. Light traveled at about 300,000 kilometers per second, but they had a much bigger problem. They believed light traveled through something called the luminiferous ether, an invisible substance filling all of space. Like sound needs air, light needed ether, or so they thought. In 1887, Albert Michelson and Edward Morley built the most precise optical instrument of their era, an interferometer, to detect Earth's motion through this ether. The idea was simple. Earth orbits the Sun at 30 kilometers per second. If we're plowing through the ether, then light traveling in the direction of Earth's motion should be slightly slower, and light traveling perpendicular should be slightly faster, like swimming with the current versus against it. They expected to see a difference, a tiny shift in the interference pattern, but that's not what happened. No matter which direction they measured, with Earth's motion against it, sideways, at different times of year, the speed of light was always exactly the same, 299,792,458 meters per second, not a fraction more, not a fraction less. This made no sense. It violated everything physicists knew about how speeds add up. If you're on a train going 60 and you throw a ball forward at 20, someone on the platform sees the ball going 80. That's basic mechanics. But light refused to play by those rules. The result sat there, unexplained, for 18 years. Physicists tried everything. Length contraction, time adjustments, new ether theories. Nothing worked cleanly until a 26-year-old patent clerk in Bern, Switzerland, decided to stop trying to save the old physics and just accept what the experiment was telling him. In June 1905, Albert Einstein published a paper called On the Electrodynamics of Moving Bodies. It was submitted to Annalen der Physik, the same journal where Max Planck had published his quantum hypothesis 5 years earlier. Einstein's paper had no references, no citations, no experimental data of its own, just 2 simple assumptions, and the courage to follow them wherever they led. 1. The laws of physics are the same for everyone moving at constant speed. 2. The speed of light in vacuum is the same for all observers, regardless of their motion. That's it. 2 statements, and from them, Einstein rebuilt our entire understanding of space and time. Here's the key insight, and this is where most explanations get it wrong. People think the speed of light is a speed limit, like a cosmic traffic sign that says 300,000 kilometers per second, no faster. As if the universe has some kind of enforcement mechanism, some force that pushes back harder the faster you go. But that's not what's happening, not even close. The real story is about geometry. Let me give you an analogy. Imagine you're walking north across a flat field. You're covering ground, moving purely northward. Your entire walking speed, let's say 5 kilometers per hour, goes in the north direction. Now imagine you turn slightly to the east. You're still walking at 5 kilometers per hour. Your legs haven't changed. Your effort hasn't changed. But now some of your speed goes east and less goes north. The more you turn east, the less you move north. If you turn completely east, you have 0 northward speed. All your motion goes sideways. Here's the crucial point. You can never go more north than north. Your maximum northward speed is your total walking speed, all of it pointed in one direction. That's not a speed limit imposed by some force. It's just geometry. You only have so much total speed to distribute. Now here's Einstein's revolution. Space and time work exactly the same way. You are always moving through space-time. Space plus time combined at one fixed total speed. And that speed is the speed of light, always. No exceptions. Whether you're sitting still, running, or flying in a rocket, when you sit still in space, all of your space-time speed goes through time. You age at the maximum rate. Your clock ticks as fast as it possibly can. You're moving through time at the speed of light. But the moment you start moving through space, some of your space-time speed gets redirected. Stolen from the time direction, pointed into the space direction, less goes through time, your clock slows down. The faster you move through space, the slower you move through time. It's a trade-off. Like turning east steals from your northward speed, and if you could somehow move through space at the full speed of light, you'd have 0 speed through time. Your clock would stop completely. No time would pass for you, ever. That's not a speed limit, that's geometry. You can't go faster than light. For the same reason, you can't go more north than north. There's nothing left to redirect. Now, this sounds like a nice theory, an elegant idea. But is it actually true? Yes. We see it happen every single day. About 15 kilometers above your head right now, cosmic rays from deep space are slamming into nitrogen and oxygen molecules in the upper atmosphere. These collisions create particles called muons. A muon is like a heavy cousin of the electron, about 200 times heavier, and it's unstable. It lives for about 2.2 microseconds. Then it decays into lighter particles and vanishes, 2.2 microseconds. That's 0.00000022 seconds. In that time, you couldn't even blink. You couldn't form a single thought. A beam of light would only travel about 660 meters, barely longer than 6 football fields. Now, do the math. Even if a muon is moving at 99.5% the speed of light, in 2.2 microseconds it can only travel about 660 meters, but it's born 15 kilometers up, 15,000 meters. It should never reach the ground. It should decay long before it gets anywhere close to the surface. But muons do reach the ground. We detect them constantly. About 10,000 muons hit every square meter of Earth's surface. Every minute. You can build a detector in a high school physics lab and count them yourself. How is this possible? Time dilation. From our perspective, standing on the ground, looking up, the muon's internal clock is running slow because it's moving at 99.5% of c. Its 2.2 microseconds of life stretches out. In our frame, the muon lives for about 34 microseconds. That's enough time to cross the full 15 kilometers. From the muon's perspective, something equally strange happens. It lives its normal 2.2 microseconds. Nothing weird about its own clock, but the atmosphere below it is length contracted. Those 15 kilometers of air, from the muon's point of view, are squished down to about 660 meters, short enough to cross in its brief lifetime. Two completely different explanations, same result, both mathematically consistent, both correct. That's relativity. This was first measured in 1941 by Bruno Rossi and David Hall. They set up muon detectors at the top and bottom of Mount Washington in New Hampshire. At the top, they counted a certain number of muons per hour. At the bottom, far more survived the trip down than classical physics predicted. The numbers matched Einstein's time dilation formula perfectly. And it's not just muons. The GPS satellites orbiting Earth right now, 20,000 kilometers up, moving at 14,000 kilometers per hour. Their onboard atomic clocks tick at a slightly different rate than clocks on the ground. The combined effect of special relativity and general relativity shifts their clocks by about 38 microseconds per day. That sounds tiny, but light travels 11 kilometers in 38 microseconds. Without relativistic corrections applied every single day, your GPS position would drift by about 10 kilometers. Your phone would tell you you're in the wrong neighborhood, the wrong city block. Every time you open a map on your phone and see that blue dot in the right place, you're relying on Einstein being right about time dilation. But there's an even deeper way to understand all of this, and it changes what speed of light even means. Forget about light for a moment, forget about photons and electromagnetic waves. Think about cause and effect. If something happens here right now, an explosion, a signal, a decision, how far can its effects reach? How quickly can it influence something else? The answer depends on the maximum speed at which information, any information, can travel through the universe. In our universe, that maximum speed is c, 299,792,458 meters per second. Not because light happens to go that fast, but because the geometry of space-time itself, the mathematical structure of how distances and durations relate to each other, has this speed built into its very fabric. Physicists draw this as a light cone. Imagine a single event, a flash, a snap of your fingers, happening right here, right now. From that event, draw all possible paths that information could take, spreading outward at speed c. In 2 dimensions, it looks like a cone. Expanding outward into the future, everything inside that cone, every point in space that the signal can reach, is your causal future, You can affect it. Below you, there's another cone pointing into the past. Everything inside it could have caused the event, could have influenced you, and everything outside both cones, unreachable, causally disconnected, not now, not ever. No matter what technology you build, no matter how much energy you have, the geometry of space-time simply doesn't allow it. This is why physicists increasingly prefer to call c the speed of causality rather than the speed of light. It's not about electromagnetic radiation, it's not about photons bouncing around, it's about the deepest structure of cause and effect in our universe. Light just happens to be massless, so it travels at this maximum causal speed. But even in a hypothetical universe with no light at all, no photons, no electromagnetic waves, just massive particles bumping into each other, there would still be a maximum speed, because the Minkowski geometry of space-time demands it. CE isn't about light, it's about the structure of reality itself. And here's one final connection that ties it all together. 3 months after his relativity paper, in September 1905, Einstein published a short follow-up, just 3 pages, titled "Does the inertia of a body depend upon its energy content?" In it, he showed that mass and energy are the same thing, related by a simple formula, E equals mc squared. That c squared isn't just a number you plug in, it's the conversion factor between mass and energy, between space and time, between cause and effect. It appears everywhere in physics, not because light is special, but because c is the fundamental constant that defines the geometry of our universe. So let's come back to where we started. You're sitting still, not moving through space, but you're moving through time, at the maximum possible rate. Your clock is ticking as fast as it can. You are traveling through the time dimension at the speed of light. The moment you stand up and walk across the room, a tiny, immeasurably small fraction of your space-time speed redirects from time into space. Your clock slows down by an amount so small that no human instrument on Earth could detect it. But it's real. It's there. The math guarantees it. An astronaut on the International Space Station, orbiting at 28,000 kilometers per hour, ages about 0.01 seconds less per year than you do. That difference has been measured with atomic clocks. It's not theory, it's fact. And a photon, a particle of light, moves entirely through space. 100% of its space-time speed goes into the space direction. 0 goes into time. The trade-off is complete. Total commitment to space. Nothing left for time. From a photon's perspective, if you could somehow ride along, no time passes, ever. A photon emitted from a star 8 billion light-years away and absorbed by your eye tonight experiences those 8 billion years as a single instant. Birth and death, the same moment. That's why nothing goes faster than light, not because there's a cosmic speed limit sign, not because some force pushes back, not because mass becomes infinite, but because the speed of light is the total speed of everything through space-time. It's all you have. It's all anything has. You're already going at sea. You always have been. You always will be. The only choice you have is the direction. Next time someone asks you, why can't anything go faster than light? You'll know the real answer. It's not a limit, it's geometry. And you've been traveling at the speed of light your entire life.